Hello. So as I promised you that I will be starting with presheaf and sheaf. So let's begin with the discussion. I hope you have all went through all the prerequisites that I have mentioned in the last session. Yeah. So mostly from now onwards the topology and category theory is going to be very useful in our discussion. Okay, so let's begin with something called presheaf. So as I said in the last introductory session that it is basically a way of transportation between transformation from a open set of topological space to a particular abelian group. So let's start with in a formal way. So for example, let us consider that we have a topological space X and let us take, for now just consider tau is a topology. Okay. Now what I will do, I will consider top X is to be the category of open sets of X. So once I have a category of open sets, that makes sense that I have two kind of objects. One is objects of top X and morphism of top X. So what is the object of top X? So these objects are nothing but open sets, and morphisms are, suppose we have u comma v, this is a subset of X, these are open sets, means the objects of the category. Then the morphism between u comma v, it is phi if v is not subset of u, and it is singleton of identity if v is subset of u. Okay, so this is how, based on the, if we have two open sets u and v, the morphisms are, there is a morphism which is exactly the identity one when only v is contained inside u, otherwise it is completely free. We can check that. It's an exercise. Check that topological space of X is a category with respect to the object and morphism defined above. Okay. Now, on the other hand, let us consider UB is a category of abelian groups. So once you have category of abelian groups, then a presheaf F is nothing but a contravariant functor from topological space X to the abelian group U. Is a contravariant functor. Okay. Now, if we break this condition, let's break it up. So if we just break it up, so what should we get? Let us consider that. So that means, so first of all, what is a functor? Functor means if you have a topological space U if you have the open set from the category of topology, category of open sets of X, let's say U, I must get f of u to be an assigned abelian group. Okay. Now, suppose you have, and what about phi? We define that phi is mapping to 0 only. Okay. This is this is by convention. We assume this one. And whenever I have V subset of U, okay, whenever I have V subset of U, then f of u, then of course, V subset of u means what? Identity morphism. It is mapping to a group homomorphism from f of u to f of v. Means basically hom uv, contravent function in case of hom uv, this is basically mapped to hom vu, right? Of f v comma f v comma fu. So the directions are getting reversed. So that means whenever I have any two subsets u and v such that v is contained in u, then there is a morphism between or say group homomorphism from fu to fv. Okay, so this is and also it should satisfy the composition law. That means if we have w subset of v subset of u, then let's say it is phi uv phi uv phi uv phi vw. So phi vw composed with phi uv, it is same as phi uw. Okay, if we have, let's say, f of u, here we have f of v, here we have f of w. So f of v to f of w, there is phi vw. F of u to f of v, there is phi uv. F of u to f of w, there is phi uw. So this diagram should come out. So this is the composition law. Is satisfied. So once you have this composition is satisfied, that means now you can see that suppose we have u. So let us have some more implication on this figure. Let us u, v and w. So where to where the identity maps are there? The identity maps are there from w to v, from v to u, as well as from u to w. So of course these diagrams should come in, right? Means if you want to see any element of w in u, first, so what you have to do? First you have to consider it in v, then you consider in u. So that means this diagram should come in. Now this commutativity is preserved in this case also. Okay, so that means the presheaf, so the presheaf, what you have seen the presheaf, is basically a contravariant functor from the topological space. The category of open sets of X to category of abelian groups. Right. Now the question is that can you give me some example? Now, okay. First of all, now the question is that why have we have chosen this category of abelian groups? What if we can take another kind of rings? So the question is that can we replace category of abelian groups by some other category? So answer is yes, we can. So in that case, suppose we replace category of abelian groups with, let's say, category of rings. In that case, the objects are going to be changed. Suppose we change it here with category of rings. In that case, we have defined that Fu should be abelian group. Then you can easily identify that this should be ring. Of course, by ring I mean commutative ring with unity. Every time I may not be mentioning this terminology, but you have to understand that what I want to mean that commutative ring with unity. Whenever we study algebraic geometry, we always consider this commutative ring with unity. Okay. And these phi UVs, initially I said that these phi UVs are group homomorphism, abelian group homomorphism, but right now I will say that these are ring homomorphism. Right? And rest of the properties will remain same. Okay. Now can you give me some example of, so example, most natural way you can consider u is mapping to f of u, where f of u is 0 or all u subset of x. It is 0 abelian group. Okay, I mean 0 abelian means it's singleton 0 only. So it is of course a presheaf, right? Or let's say any constant sheaf. Sorry, not sheaf, constant presheaf. Let us consider that U is mapping to particular abelian group A for all U is subset of X and U is open. It is a presheaf. Also, we can consider presheaf of, let's say, C XR. Okay, and let's say X equals to R. Yeah. Let's say, okay, not now. Let's just consider X equals to R. And we are considering U to CU1. Okay, that is set of all continuous function. In fact, you can choose C infinity R as well. So, but we are, so let us consider C infinity I. So it is set of all infinitely differentiable real functions. So these are some examples of presheaf. Let us have some terminologies. So if you take S belongs to f of u, let's take u is subset of X is open set, and any element of this f of u we call it as section. Okay, and if we take phi u of S, usually denote it as S restricted U, it's called restriction map. Okay. If you, so one thing that not phi u, let us write it as phi u v of S. If you see Harshon, you'll find that it has been replaced by rho uv. So you can, whatever you write is completely fine. If you are familiar with phi uv, I just written phi uv because we usually denote the group homomorphism with phi. That's why I've written with this one. If you can use rho uv as well. Okay. Now, what is a sheaf? Sheaf is more generalized version of presheaf. So, for example, suppose that X is a topological space and we have it with sheaf, let's say F defined on X, capital X. So F from topological space of X to a abelian group, this is a presheaf. So when we say that it is a sheaf, so a presheaf is said to be a sheaf if the following are satisfied. Number one, suppose we have an open cover of any particular open, suppose this is open set and you have an open cover, this open set such that S restricted at Vi, it is 0 for all I belongs to capital I. Okay. Then what we can say? Then S is itself 0. Means that phi u Vi of S is 0 for all I belongs to capital A. Note that Vi is subset of U, right? So phi u Vi, this is mapping from f of u to f of Vi, and this is for all I. This such phi u Vi may exist. Now, if for every small I, S is mapping to 0 in each f of Vi, okay, then S is itself 0. So you can have implication here. For example, suppose we have function f from u to r, and you can be written as small I belongs to capital I Vi, such that f restricted at Vi, this is 0 map. That means if we restrict f at every Vi, it is 0. So then from here you can easily conclude that f is itself a 0 map, right? Because if you take any small x belongs to capital U, then of course small x must belongs to V of Vj something for some j, and phi of Vj itself 0 is given. That means fx has to be 0. That means fx is 0 for any u x. So that is the same implication is happening here. And secondly, suppose we have u is basic, it is an open cover of Vi such that, so let us see that S restricted at Vi intersection Vj, okay, not like this, okay, suppose such that Vi and that Si belongs to f of Vi. We have some sections from each Vi such that if we restrict each section to Vi intersection Vj, these are agree in the intersection. That means if we have, let's say, f of Vi here and another f of vj here. We have a collection of sections, let's say si, from vi and sj in vj. Now see that vi intersection vj is subset of vi as well as vj. So there is always a group homomorphism from f of vi intersection vj, f of vi as well as f of vj. So we denote it as rho vi intersection vj, and this we denote as vj comma vi intersection vj. Okay. Oh, sorry, I'm very sorry, that notation should be changed here. From here to from here. Now it's saying that both the images of si and sj are same in this particular abelian group. In that case, there exists small s belongs to f of u such that s restricted at vi is si. That means in that case I have some, let me take it down. In that means we have some, so here I have u, right, and f of u to f of b, always there are maps rho u vi, rho u vj. Now there is a map small s in f of u such that it agrees at both the components. Okay, so the entire diagram should commute. So you can easily figure it out that it is somehow similar to gluing lemma in real analysis, or let's say topology. Okay, that means it is suppose we want to define a map u from u to r, but we are given a basic let's say open cover vi. So it is enough to define each fi from each vi to r. These are continuous function or any mapping. Then we can glue them up. Then what we will do, we will just take f is a mapping from u to r such that f of fi of small x is basically f of x is basically fi of small x. So note that I haven't said that each open components are disjoint. So as these two are not disjoint, that's why we need that they should agree in the intersection. Otherwise, suppose we have si from here, sj from here. If he is giving some another elements in this f intersection vj, in that case we cannot say that this diagram should commute. Okay, that's why it is important to have the condition that they should agree at the intersection region. Okay. Now this one observation. That from the definition is very clear that every sheaf is presheaf. But what about the converse? What about the converse statement? So is every time, suppose you have a presheaf, you note that in presheaf the conditions were very less and very flexible. For example, we just need to define a contravariant functor, but it need not mean that, it did not imply that it should satisfy the gluing condition as well as the localized condition. That is, 0 condition that I have written there. So can you give me an example? Anyway, so it is not true always. So can we give some example? So counter example, you might have remembered that once I have written it here constant sheaf, I immediately raised it up because this is a counter example that if we take a constant presheaf, it is not always a sheaf. So let us see how to do this. So that is a counter example that is not a sheaf. So why it is not a sheaf? For example, let us consider that let us take x to be a, b, c and give it discrete topology. Discrete topology means each singletons are open, right? Now, so take A belongs to category of, let's say, object of this category of abelian groups such that each singleton, non-zero singletons are, open set that is mapping to A. So B is mapping to A and correct. Now let us take it is U1, so U2, U3. Okay. And we define that let's say A1 belongs to capital A and A2 this belongs to capital A. Let's take, so consider that A has more than two elements. So A1 and A2 both are same and A1 is not equals A2. Now if we consider that, let's say A1, what is E1 restricted U2? Basically A1 intersection phi. So it is of course 0 because f of phi is 0, right? Now again A2 restricted U intersection U2, this is A2 restricted phi is 0. Okay, so let us take two elements only. It is enough to take two elements. Let us take a capital X is a discrete topological space with two elements, and yeah, that's fine. Now if we consider that, so let constant presheaf is sheaf. So as it is constant presheaf is sheaf, so what we have defined the gluing condition is that if they agree in the intersection, there is an element in the global section, so the restriction of the global section is that each component of S, like SI, like this kind of things. That means if it is a sheaf, then of course there exists some small a belongs to capital A, such that, because what is f of x? F of x basically capital A, right? So small a belongs to capital A, such that A restricted at U1 is A1 and A restricted U2 is nothing but A2. Now each restriction maps are nothing but identity. In constant presheaf, its restriction maps are identical. So that means A has to be A1 and as well as A has to be A2. But as we have defined, we have chosen A to be if we let's say abelian group with more than 2 elements, that means A1, and of course we have inserted the condition that A1 is not equal to A2. That means here is the contradiction. So every time the constant presheaf may not be a sheaf. In fact, there are some more presheafs that is not a sheaf. We'll study something called direct limit of sheaves, and this is not also a sheaf. It's a presheaf but not sheaf. So for you, it's an exercise to check that the constant presheaf is sheaf or not. Exercise that is sheaf or not. Okay. And also to check that this let us consider X topological space, and I am defining this small b belongs to capital X is a point. So what I am doing, I am defining a contravariant functor in the following way, that IP is a contravariant functor. Let's say IP, and let's say A is a abelian group, is fixed. It is fixed, and if we define it, IP of A is a mapping from U, let's say let's say object of topological space to abelian group such that IP A of U, this is 0 if P does not belongs to U, and A if U belongs to U. Okay, so check it is presheaf or sheaf. For information, this is called something called skyscraper sheaf. Okay, so we have briefly defined what is presheaf and sheaf in this lecture. Next day we will define something called sheaf homomorphism. Of course, I will solve this exercise also. If you just try for your own, up next class we will solve this one, these two exercises. And also we will study something called what is the morphism between sheaves, stocks, and something called sheafification, because we have already decided that every presheaf, it may not be a sheaf, but we can always have a unique sheaf structure that is obtained from a particular presheaf. That is called sheafification. So we will define that sheafification, morphism of sheaves, and stocks of sheaves in the next series. Okay, thank you very much for your patience.